Okay. Hi, everyone. Good afternoon. I hope you're all enjoying your summit so far. You give a cheer or something if you are. Fantastic. Hi, my name is Paul White, and I'm going to be giving you a sort of 60-minute, maybe 70-minute talk this afternoon, I hope, on understanding parallel query execution. So if you're in the wrong room, now would be a good time to stand up, wave, and get to where you need to be. Okay, so this is DBA 313. I apologize in advance. I'm probably going to wander around a bit because I get terribly nervous before presentations and the energy tends to come out in my legs. But thanks everyone for turning up. It's so great to see such a huge number. I was expecting maybe 10 people. So this is great. The only other thing I'd say is this is a brand new presentation for me. It's my first time at PASS. It's my first time giving this presentation. If you want to see me give a more polished performance, I'll be doing a half day on Friday, which I've done many times before. So please bear with me today if anything doesn't go quite according to plan. Okay, is everyone in? Yeah? Okay, cool. All right, so a little about me slide. I don't really like to do these, but I guess some of you will want to know who I am. I live in New Zealand, starting at the bottom left there. I blog at SQLblog.com. It's a site with a lot of very good bloggers on there. It's a bit of an honor to be writing in the same place, to be honest. Sorry? Oh, I'll speak up, shall I? Is that better? Is that better? A little bit. It sounds really loud up here, if that helps. Okay, I'll stand here, shall I? Is that better? Okay. Yeah, so I blog at SQLblog.com along with a lot of other fine bloggers, Aaron Bertrand, Kalen Delady, Adam Mechanic, other people like that. So if any of you do know me or have heard of me, it's probably from my blog, I suspect. So I write about just the core database engine, really. Query processor, query optimizer, query execution, and a little bit recently in the storage engine, which is a new thing for me. You can follow me on Twitter if you like, at SQL Kiwi with an underscore. Somebody else has got the one without the underscore, so be careful on that. I do tweet from time to time. What else? Oh, you can email me after the event if you like. I'm always happy to hear from people to say how much I sucked or how much they enjoyed it or meh. So that's always good. It's a public email, so please don't spam it. It gets kind of tedious. The other thing I wanted to highlight was a little site called Database Administrators, or Database Administrators. It's a Stack Exchange site. It's not that well known, but there's a lot of really good people go there. So if you know how to ask a good question about SQL Server, you'll get a brilliant answer, I guarantee it personally. Okay? So not associated with it, I don't make any money from it or anything, but I'm just a fan of the site. It's like Stack Overflow, but specifically for databases. Okay, not just SQL Server, so Oracle questions, MySQL, anything else. Okay, that's about me. Enough of that. Let's get into the important stuff, which is counting jelly beans. So this is a 300 level talk, but I do start off sort of level 100 or a little below, and we sort of move up towards 400 maybe, and I'm hoping to average around about 300, if that's okay. So parallelism. I want you to imagine that instead of a small standard clip art from PowerPoint with a jar of jelly beans, I actually had a massive jar of jelly beans here on the table. I was going to do that, but there are issues with customs and baggage allowance and things like that. But I want you to imagine I've got a huge jar of jelly beans here, and it is important to the world that we know how many jelly beans are in that container. Now, I could count them myself, and I estimate it would take me about 8 minutes. Yeah, I'm pretty good, okay, but I'm pretty average at counting jelly beans. It would probably take me about 8 minutes. But if I could get 8 of you to come up and share the task, we could get it done in 1 minute. Make sense? Yeah, pretty obvious, right? So the way I'd probably arrange that, thinking of SQL Server, is that we would have the jar and a single bean scoop that people could dip in, take some beans, take them to the side, count them, keep a running total, and at the end you all give your running totals to me, hopefully together, I add them up and there's your grand total. Okay, so overall, we've improved the response time of that count the jelly beans query 8 times. Fantastic. The total effort spent is roughly the same, because 8 people work for 1 minute rather than 1 person for 8 minutes. But what if we had lots of jars to count? And I know there's a lot of you here today, more than I was expecting, but if I had lots and lots of jars, we could get to a point where there weren't enough of you to help me count the beans. We would be running out of workers. It's a theme I'll return to later in the talk. Okay, so that's counting jelly beans. If you want to count jelly beans with SQL Server, you can't do it directly, but you can count rows in a table. So this is a simple count star query from the favorite AdventureWorks transaction history table. And SQL Server on this occasion, in this query plan, has decided to use one worker, one person counting the beans. So scan the table, count the rows, return the result. Brilliant. But transaction history is not a very big table. If it was a very big jar of jelly beans, a very big table, then SQL Server is likely to choose a parallel plan. Okay. So that looks roughly the same. There's an extra stream aggregate in there, which I'll talk about in a bit. And there's a lot more rows. I don't know if you can see it on the screen, but there's 31,263,600 beans in that particular table. And this is based on Big Transaction History, which is a script that I ripped off from Adam Mechanic. He published on his blog a little while ago a way of expanding AdventureWorks up to a bigger size for demonstrations like this, because normal AdventureWorks is not really big enough to invoke parallelism. Okay. So, but for a moment, I want you to imagine that there was no parallel query support in SQL Server. All you could do is run serial queries. Okay, and there are products around like that. I think Postgres is still serial. MySQL certainly is, I think, right? Some nodding heads. Okay. So what we could do, if we're feeling creative and we really wanted to count the rows in our table more quickly than we could do on a single thread, is we could write a query and break it up into ranges and run it on different connections in Management Studio. Yeah? It's a bit like the idea of spreading the work 8 ways. So I could rewrite my query as, say, 4, because that's all the space I've got for on the screen, to count the rows from this table where the ID is between some number and some other number. And I've arranged the IDs so that we'll end up counting all the rows. And that would give us 4 concurrent serial plans running in SQL Server. And being the multitasking product that it is, they'd all run concurrently, probably on different CPUs, and we'd get 4 results, which would then add together recurring thing. Okay. Now that does rather assume that the data is evenly distributed across the IDs in the table, because I just broke those 4 ranges up arbitrarily. But what I did do was run a little query like this, to say, give me the minimum and the maximum IDs in that table so I could work out what my ranges would be for my 4 threads. Okay, and that gave me a plan like this. Now, it's a little bit of a diversion, but I wanted to mention this plan because it's a really good example of how SQL Server, and the optimizer in particular, can rewrite your queries for you to make them go much faster. So you'd think taking the minimum and the max of an ID in a table, it would just scan the whole table and take the first and the last ones, right? But what it's done here is broken it up into 2 steps. So what it says is, if you want the lowest ID on the table, and I have an index that's sorted on ID, what I can do is scan that index, and the first one I get to will be the lowest. Or I can scan it backwards, and the first one I get to will be the highest. So that's what it's doing here. These 2 table scans here are not full table scans, and that's something a lot of people don't appreciate when they see a scan in a plan. It's not always bad. This is the most efficient plan for this query. Okay, so the top cluster unit scan is a forward scan, starting at the lowest ID, and the bottom one is a backward scan, starting at the highest ID. And the top iterator there just takes the first row it finds. The stream aggregate is interesting. It's there to produce a row if there are no rows in the table. Sounds weird, right? But that's what scalar aggregates like. So an aggregate without a group by clause is a scalar aggregate, and it always returns a result. You do select count star on an empty table, you expect a single 0 result back, right? Different with vector aggregates, which have a group by clause, which will become important later on. Okay. Now SQL Server doesn't. Yes. Yep. Yep. Okay, so the question was, how do I know that it's not reversed and the top one's not doing the max and the top one's not doing the min? Because I checked it. But thank you for that. Okay, so SQL Server doesn't quite do that exactly. And what I've been talking about so far is a lead-in to how SQL Server does parallelism. And that's the last time I'm going to say parallelism. It's too hard. I'm going to say parallel execution. Okay. It doesn't exactly split it into 4 ranges, hoping that between the min and the max there's an even distribution of data and there's nothing either side. What it does do is cooperatively scan using a demand-based scheme, which sounds fantastic. And it uses key-based ranges for parallel seek. So looking at our parallel count star on the big transaction history table plan, that is actually that. Okay, so that's what you see in Management Studio or in SQL Sentry Plan Explorer. This is what's really happening. Okay, so there are 4 independent, serially running scans that cooperate to scan the whole table. And when I say cooperate, I mean the storage engine has a parallel page supply, a key range supply thingy with some synchronization, so that one of the 4 threads will read a row, but no other thread will. Yeah? So there's a bit of synchronization there to make sure that you get the right result. Does that make sense to anyone? Please raise your hand if it doesn't. Okay, cool. All right. Now, I want to mention quickly execution context. Yes?
So,
previous slide?
When it is synchronizing itself, is it synchronizing itself by range?
Right. Let me nip back.
Oh, yeah, base range, I'm sorry.
Good question. You're asking the question was how is it synchronizing? Well, in the case of a scan, it hands out batches of pages on demand. So the first thread that needs some work to do gets a batch of pages. If it's a seek, then there's some math and science in there to work out what the key range is. So it does do a little bit, but the ranges are much smaller. So the effect overall is to distribute the work amongst the threads as soon as they need it. Okay, thank you. So execution context. You may have seen this in some DMVs or in some of the books online literature talking about execution context. But an execution context is just the same thing as I've been talking about in terms of separate connection if we were using manual parallelism. Parallel execution. Promised I wasn't going to do that. So an execution context is just a lightweight version of a separate connection. Yeah? The way I visualize parallel execution is there being separate sessions running serial queries, but those sessions are optimized into a thing called an execution context. Okay? Now, in this particular case, I ran the test at DOP4, degree of parallelism 4. So there were 4 execution contexts, 4 separate connections, if you like, on the scanning and stream aggregating side. Then there's this mysterious thing in the middle that doesn't have any colored borders to it, the gather streams, which I'm going to talk about next. And then finally, there is the adding together of all the partial results to make a final total. I should probably mention, actually, that final section, the one on the left with the select icon, it's got a lot of names. Some people call it the coordinator thread. Some people call it thread 0, which is how it's identified in Management Studio. Some people call it the root thread, which will make anyone from New Zealand laugh. Root has a different meaning. But I think I'll call it thread 0, if that's all right with you. Okay? It's the final serial thread that your connection is running on. Because obviously, if you run a parallel query, the results have to come back to you, the single-threaded client, at some point. So there's always a final serial section. There's always a thread 0. There's always a root thread or a coordinator thread. All good? Okay. So these things always execute on a single thread. I just want to make that point absolutely clear. There's no parallel execution within execution context. They're always a serial thing. It makes them much simpler and easy to understand. And there will be the DOP context per parallel branch. And I haven't mentioned what a branch is yet, but I will do shortly. But just bear in mind that there are 4 contexts in use in this particular case because the query is running at DOP4. Okay, so there's 5. There's an extra one for the final serial thread. All right. So now, if there's no burning questions on the first section there, I'm going to talk a little bit about exchanges. Something else that has 2 names and is going to force me to use that word for a second time. Exchanges are the internal name, and I find much more intuitive name for the parallelism operator in query plans. Okay? They're called exchanges because they exchange data across threads. but that's what we're coming on to now. So there's three varieties of these fellas. The exchange operator. It marks the boundary between branches of the plan. And there's a gather streams, a repartition streams, and a distribute streams. You're all familiar with these? You've seen these in query plans? Don't be shy, say yes or something.
Yes.
Good on you, good on you. Okay, and they transfer data between execution contexts across thread boundaries effectively. And these three can split, combine, or repartition streams of rows. And by split, I mean it can take a serial stream and split it out amongst worker threads. Repartition can take data that's already in different threads and move them onto other threads within the same group. And gather streams, there's always a final gather streams to get everything on multiple threads back to one thread. All right. Now these things have a sort of sub-operation to them which decides how they route or route rows between threads. And they also provide a certain amount of buffering and flow control. This is why exchanges need memory. So whenever you have a parallel plan with exchanges in it, there will be a certain amount of memory grant associated for the buffers that are inside these exchange operators. Okay, they're just buffers. They're not terribly big, and there's not terribly many of them. But again, we'll talk about that in a bit. The final thing that an exchange operator can do is to preserve an incoming sort order. So it'll never sort the rows itself, but if there's an incoming sort order that the query execution engine needs to remain sorted, perhaps because it's going into a merge join or a stream aggregate or something else that requires sorting, it can operate in a mode where it preserves the sort order on the incoming threads. Again, more on that in a minute. Okay, so a picture of an exchange on the inside. They basically look a bit like this. This is a gather streams. This is the one we've seen so far in our count star example. So there were four threads providing partial counts. There's some buffers inside the exchange, and there's a separate thread on the consuming side. So these are all separate workers, okay? So this is where we get our 5 threads from. In the case of... Yeah, okay. So they execute independently on different threads. The producer, this is the interesting thing about the exchange. The producer is one of the only operators that pushes rows from right to left in a query plan. And it does that via an internal mechanism called ports and pipes, or CX pipes and CX ports, as they're known. So a producer gathers rows from its source, pushes them into a port and a pipe, and they end up in a buffer. And that buffer is a CX packet, is a packet, okay? So if you've ever seen CX packets weights or something, and I'm going to get into this, that's what it is. It's one of these buffers either becoming full or it's empty. Yeah, so someone wants to put some data into a buffer, but it's full. It's a packet weight. Somebody wants to empty a buffer. Again, you get a packet weight. Okay. And it also applies a sort of basic flow control. Because there are only so many buffers, obviously a fast producer thread could be stuffing buffers in, but it gets to a point where it runs out of buffers, so it'll stop and wait on CX packet. And that's your basic flow control. Now, a repartition streams operator that moves data between... Yes, sorry. Yep. Yep. So the question is, how can you optimize away CX packet? I've got a couple of slides just in a moment on CX packet that I hope will answer that question, but please raise your hand again if it doesn't. Okay, repartition streams is a little bit more complex looking. There's a lot more lines, but essentially it's doing the same thing. So packets of rows are coming in on the producer side on 4 threads. There's some buffers in the middle, and those producers can pass a packet of rows to any one of the consumer threads on the consumer side. All right? Now, how they decide to route these rows depends on the partitioning scheme. Now, it's not that partitioning, it's not table partitioning, it's got nothing to do with partition functions or partition schemes or anything else like that. It's just another reused term within SQL Server. Okay. So the partitioning scheme for an exchange defines how producers send packets of rows to consumers. Okay. So this is an important point. It's relatively expensive to move things between threads. Okay, so they don't do it a row at a time. They assemble them into packets and then move the whole packet across thread boundaries. Okay, and it's the producers that run the show. Okay, so they have a sub-plan that they're getting rows from. They assemble them into packets, push it across this pipe and this port into a CX packet, and that's how the thing proceeds. All right. So partitioning only applies to distribute, one thread to many, or repartition, many to many, not many to one, the gather streams partitioning. Because obviously there's no partitioning to do in that case. They all end up on the same thread, right? Okay. So there are five different partitioning schemes. And if you hover over an exchange operator in Management Studio, or look at the properties in the plan tree, I think it is, in Plan Explorer, you'll see that the exchange has the property of either broadcast, round robin, hash, range, or demand. Okay, so I'm not going to read them all out, but essentially broadcast sends one packet to all consumers, and round robin says, right, you have a packet, you have a packet, you have a packet, you have a packet. Okay? General concept makes sense? Yeah, good. Okay, so all of these fill packets up and pass them across the pipe, except for demand. And demand is a strange one. You only really see it in, ironically, partition table queries, where they've got two tables joined together on the same partitioning scheme. So demand works backwards. So the consumers demand a row from the producers and drag it across the exchange. Yeah? The normal mechanism is producers push, but for demand, it's a row at a time, not a packet, and they pull. Doesn't scale well in general. That's why it's not used quite so widely as the others. The one you'll see most is probably hash partitioning, where it evaluates a hash function to determine which consumer to send a particular packet to. Okay. Now, I mentioned that exchanges can, optionally, preserve the order of rows flowing through them. The distribute streams, if you think about it, always preserves the order. If I've got an ordered stream of, well, not jelly beans, but rows or something, and I'm passing them out to four of you, in just as I feel like it, you're going to get ordered streams. Yeah? If you think about it, the order will be preserved without me doing anything special. Okay. So an exchange that preserves order, and remember, I want to emphasize it does not sort itself, is known as a merging exchange. It's a technical term, I suppose. It reminds me of merge join and the ordering that comes with merge in that scenario. But yeah, it's called a merging exchange. So this is an example. I've got three threads, three on the producer side of an exchange, and they have an order to them, ascending order of integers on each thread. So across threads there could be a different ordering, but I hope you can see that each of those is, if I've drawn it correctly, are in ascending order. And with this exchange operating in a merging mode, preserving order, the output will look something like that, a typical output. So it could take the 110 from the blue thread, then it looks to find the next highest one that's available to it. That's the 120, the 130, the 140, 150, 160. Now, as you can imagine, there's a bit of an overhead to doing this, because if it wants to preserve order, it has to check, in principle at least, each thread coming in to see which value it's got, to make sure it doesn't pass something out of sequence. By contrast, a non-merging exchange at the bottom there is free to produce those rows in any order it likes. Okay? So if the query plan doesn't need sorting to be preserved, the second option here is very much more efficient, because it can just take whatever it finds from any available producer and start beaming it back to the client. Okay. Hello. Okay, question is, what sort of query can result in a merging exchange? Typically, a query with an order by, or a query that's using a merge join, or a stream aggregate, or anything else that after the exchange requires a sorted order. If that sorted order is provided by an index or some other operation further up or further down the query plan, the exchange needs to preserve that sort order. Otherwise, you'd need a fresh sort, which would be expensive, right? Yeah. So question is, to repeat for the recording, wouldn't an unordered merge followed by a sort be cheaper? Yeah, so the optimizer does consider both options, but generally speaking, sort, especially multi-threaded sort, is an expensive operation, even more so than a merging exchange. So it will generally. That's a very good question, actually, because there are some issues with operating at higher degrees of parallelism, where the exchange can become more expensive, and you might see an explicit sort, yes. Okay. All right, branches. I promised I would talk about and define what a parallel branch is. So I've got a slightly more complex query here. Again, AdventureWorks, it's just the product table joined with the transaction history table on the natural key. And for each product, we want to know how many we've got, or how many rows of history we have. And it's only for products between 1,000 and 40,000. The specifics of the query aren't important. It's the plan that I want to look at. So this is a more complex plan. And I've shaded it in colors to identify the separate parallel branches in this query. Now, as I mentioned earlier, the exchange operators mark the boundaries between branches. Okay? So I hope you can see on that diagram the boundaries between the shading, the different colors of shading, are marked by an exchange operator. And that exchange operator will have a producer on the right-hand side, collecting rows and stuffing them into pipes and packets. And on the other side, there'll be a different thread, or many different threads, acting in a consumer role, consuming rows from the exchange. All right. Now, it's a reasonably complex plan with 4 branches to it. So we're going to look at them one by one, after I've mentioned that there are a degree of parallelism threads in each parallel branch. So if I'm running at DOP4, there'll be 4 threads in each colored zone, 4 different threads in each colored zone, generally speaking. And there's always this one final serial branch that I talked about earlier. Okay, and this example, as I work through it, is using DOP4. So, branch 1 I've identified as the sort of bluey, sort of grey one there. It's just a simple plus index seek on the product table to find the range of products that we're interested in. So there are 4 threads here, busily cooperating to scan that range. We talked about the cooperative range scan earlier on. So they look a bit like this. This should be familiar from the earlier slides. 4 serial seeks cooperating via this synchronization to only scan each product once. So the first one will be reading rows, and as they come back from the storage engine, it'll be assembling them into packets and putting them in the exchange. Same with thread 2, thread 3, and thread 4. But these 4 things are completely independent. They're just as if you'd run them on different connections. Okay? That's the mental image I'm trying to get across to you here. So we have 4 execution contexts, not connections. There are execution contexts. Very quick and easy and cheap to create for SQL Server. It does cache them, but it's quite happy to lose them out of memory if there's memory pressure, because it can create them from the query plan pretty quickly. I mentioned the cooperative key range scan they're doing here, and they're pulling the rows into the producer side of the exchange. Okay, so branch 2 is on the bottom there. It's very similar. We've got cooperative key range scan on the transaction history table, in this case. Again, in the range of products that we're interested in. 4 more worker threads, 4 more execution contexts. But there's an extra thing here, which was the extra stream aggregate we saw right on the second or third slide. And that's doing a partial count aggregate. So each thread is counting the number of rows it sees per product ID. Now, the way rows are distributed by the parallel seek, they could be on any thread. So each thread could get some for product ID 3, some for product ID 10, and whatever. So all they're doing is giving their own local count from the rows they've seen. Okay? But there's a particular advantage to this, which is that it reduces the number of rows. I'm not going to zoom the screen, but it takes it down from 5.5 million rows to about 4,500 rows per thread, because it's grouping by product ID locally to that thread. So that means there are many fewer rows to move across the exchange. And moving rows across the exchange can be expensive. So this is a good optimization. Branch 3 is the complicated one in the middle. So it has two two inputs to it on the right-hand side, operating in consumer mode, and it is feeding rows ultimately on the producer side of that exchange on the far right. So again, we have 4 more worker threads. That's a total of 12 so far. Even though we're running at DOP4, we have 12 threads. The exchanges are using hash repartitioning, and they're using the same hash function. So on the product table seek, if a product ID value hashes to thread 1, on the bottom seek, using the same hash function, the same product ID rows will go to thread 1 also. Okay, it's very important to get correct results that they use the same hash screen. The hash aggregate at the bottom is summing up the partial aggregates from the previous zone that we saw. Okay, so there were 4 partial counts before, so they could all have a view on how many product ID 10s it's seen. This simply adds it together, a little bit like the first query that we saw. Now, this is, if you can get this bit, this is all there is really to understanding parallel query plans. Those 2 exchanges on the right-hand side, the top thread, the blue one, is coming from the blue branch. The green thread one is coming from the green zone on the bottom branch. Okay? Feeding into a serial hash match aggregate and then into a hash join. And because the hash functions are the same, they're guaranteed that all rows that should be there will be there on the same hash join. Okay? And there's 3 more of those, 1 for each combination of threads. But again, this is all serial. As far as they're concerned, the query plan north and south of where they are is not parallel at all. They don't know, they don't care. They're running in serial. And finally, we have branch 4, which is the final serial thread that simply gathers results together and returns them to the client. Okay? And this one is not a merging exchange because our query didn't have an order by or any other particular reason to preserve the sort order of rows. And this exchange will just be gathering the rows produced by the 4 producers from the orange zone, those 4 worker threads, putting them into buffers, reading them off on a consumer thread, and passing them back to the client. Okay. So just to summarize that more complex plan, the execution engine has reduced the cost of the exchanges by doing a partial aggregation up front, a count per thread, so it moves fewer rows across the exchange. The hash join and aggregate in the plan are going to require a memory grant, because they always do. There's going to be more memory used for the exchange buffers, the CX packets. And with a total of 3 parallel branches, the 4th one serial, we might need 12 worker threads to run this query plan, even though we're running at DOP4. But it turns out there are only 8 threads reserved by SQLOS and used in this particular query. And the reason is that hash join always reads all the rows from its build input, the top one, the blue zone, before it moves on to process its probe input, which is from the green. So those 4 threads that it used for the blue zone are guaranteed to have finished all their work by the time the hash join transitions into probing. Okay, so it can reuse those 4 threads for the green zone, and that's typically what it does. So instead of 12 threads, we get 8, with 4 of them being used twice. Okay, any questions on that little section? Okay, so the question is if whether worker threads are agnostic to each other and whether they run independently. The answer is that ideally, yes, they would. And that's one of the important things. There is a slide actually later on where I talk a little bit about that. But yes, for really good parallel performance, you want all these things to be completely independent. So as far as they know, they're the only query on the system. They're not waiting for anything else. Now, obviously, the interactions at the exchanges, if the buffers become full and things like that, then there has to be coordination there and things can go wrong. But yes, in general, they are completely separate and independent, oblivious of the existence of the other threads in general. Anyway. Is there another question? Yes. I'm sorry, I can't hear you. Right. So the question was, is this the best query plan for this query? And if so, what settings have I used on the table? No, it's not the best query plan. Or, it depends. I had to say that, right? Do you mind if I move on? Because I've got a lot of stuff to get to. I'll remember where you are. Maybe we can talk later. Okay, so one question, before I get to this question of whether that's the optimal plan or not, is why would the optimizer ever choose a query plan that uses lots of threads? It's going to use more workers, right? It's going to use more resources. It's going to use extra memory. There are extra exchange operators in the plan. Why would a cost-based optimizer that's looking for, a good plan pretty quickly, why would it choose a parallel plan? And the answer is that the costing model is modified. Okay, if the optimizer gets as far as considering parallel execution, it essentially reduces the CPU cost of each operator, the estimated CPU cost, by the estimated degree of parallel execution that's going to be available to it at runtime. Okay, so I've got an example of that. The I/O cost, strangely enough, is not affected in the costing model. So what they're saying basically is if you have multiple CPUs, they don't help you read data from disk any faster. That's not necessarily true on your hardware, but that's their model. Okay? The model is a model. Okay? It works pretty well for most people across the planet, but this is one of those slightly less realistic things, I think. I think if you've got more CPUs, you can drive I/O harder if your I/O system's reasonably decent, right? Okay. The estimated DOP that it uses is always half, say always, pretty much always half the number of logical processors available to SQL Server at the time the plan is compiled. Now it does that because it can't assume that it's going to have unrestricted access. Say you've got 8 cores, it can't assume that all 8 are going to be free, or there's going to be enough workers available on the system to run this query at DOP 8 every time. So it takes a guess and says, okay, I'll cost this on the basis that I've got 4. Okay. Now, obviously down at DOP 3, it doesn't half it to 1.5, but it just goes down to 2. Now, against this cost saving from the optimizer's point of view, you're saving CPU cost by having stuff done on different threads concurrently. You've got the extra cost of the exchanges to pay for. Okay? So there's a bit of a balancing act to go on here to see whether you're going to get a parallel plan or not. As an example, our original count star query from Brig transaction history, I've listed the estimated CPU costs of the parallel stream aggregate and parallel index scan at different DOPs. So you can see at DOP 1, taking the index scan, it's 34.4 cost units. At DOP 2, it's halved to 17.2, and then halved again at DOP 4. It's not halved again at DOP 8 because my machine only has 8 logical processors. Okay, so it's only it's going to estimate 4 because it's half. Okay, yeah. And the same goes with the stream aggregate. So on the cost-saving side of the ledger, we've got these operators that have their CPU costs reduced. On the expense side of the ledger, we've got extra costs involved in the exchanges. And the optimizer weighs those things up, considers lots of different plans, and hopefully picks the one that looks cheapest to it. Well, it will pick the one that looks cheapest to it. Whether that actually turns out to be cheapest or not is another question. All right. So the question of whether that was the best plan. I want to talk about parallel nested loops. Okay, nested loops have a bad name, and you're all entirely wrong about it. Okay? So we all talk about set-based being good and iteration being bad and things like that, and don't write cursors and don't use while loops and things like that. And that's all generally good advice. Yeah? Write set-based SQL when you can. But just because the query processor decided that a nested loop join or a parallel nested loops join, which is iteration, it's for each one of these, do one of that, that's still set-based in my way of thinking. It's just an implementation detail. Okay? We can argue about that later, over coffee or whatever if you like. But for parallel nested loops, the optimizer does not do this halving or this reduction of CPU cost on the inner side of the join. All right? It doesn't. Yeah? It doesn't like parallel nested loops plans. It's biased against them. It aggravates me. So this was a real question I had the other day. I had someone say, on my system I had a lot of key lookup plans, and we increased the server max stop, and they all went away and got replaced by hash joins the next time the query plan compiled. Why is that? Why would just changing max stop do that? And the answer was that it changed the costing model. Yeah? So costs could be, when the max dot went up, the increased halving, quartering, eighthing, or whatever, made the hash join plan cheaper. Because the parallel nested loops wasn't being cheapened on its inner side, but the hash match was benefiting from this reduction in CPU cost on both its inputs. Yeah, so for higher DOP plans, or higher DOP systems, you are more likely to get hash joins and maybe parallel merge joins, but they've got issues of their own, rather than parallel nested loops. And that's a shame, because these things can perform really well. And I'm going to force the optimizer to come up with a parallel nested loop plans for our query that does the count per product ID. So the first thing I've done is to create a little temporary table called products. But I'm just going to put the products in there that we're interested in. So product IDs 1,000 to 40,000 go into this temporary table. Cool. And then my second part of the query, so I've got the extra cost of creating a temp table and writing rows to it. I'm prepared to do that. And then the second query, I'm going to use cross-apply, which is iteration, right? It's a correlated join. So it says, for each product ID, if you're a .NET programmer, you might recognize this as sort of like a for each construct. So for each product ID, go to the transaction history table and count the rows for that product ID. Yeah? Sounds less set-based, but to my way of thinking, this is still a set-based query. So I rewrite the query like this, and we get a new query plan. Okay? That's just the same query text and a different plan to look at. There's only one exchange in this query plan. All the repartition streams have gone. Yeah? We've just got the final gather streams. And you'll always have a final gather streams in a parallel plan, right? Because they've got to be taken back to the one thread for the client. But all the rest of it seems to be running in parallel without any extra work. So we've saved the cost of some exchanges here. So the rows are distributed across threads by that parallel scan thing that we talked about earlier, and that's the only distribution that goes on. There's no other repartitioning, moving data between threads. If the clustered index scan does a good job of distributing rows across the threads, this will be a good plan without any more repartitions. Now, I'm not sure I've got as much time as I'd like to get into this inner side thing, but the inner side of even though it's got the same parallel icons, the little yellow dot with the arrows in it to say this is running in parallel, it's a different sort of parallelism on the inner side of a loops join. Yeah? It's a different type. What do I mean by that? It's actually really hard to explain. The best I think I can do is to say, it's like this for each model, okay? The index seek on the inner side of that nested loops join cannot be a cooperating range scan. It can't, if you think about it, because the correlated parameter, the product ID, will be different for each thread. We might get product ID 1 first, go and find the transaction history records for that, then 2, then 3, then 4. There's no single seek that cooperate to do that. So what you effectively get is parallelism on the inner side of a loops join by running multiple serial executions with a different correlated parameter simultaneously. Okay? Now that takes a bit of getting your head around, but it's a very important difference. And if you want to see how important that difference is, go to Adam Mechanic's session, his Spotlight session tomorrow morning, where he's got an awesome demo of exactly how powerful that is. I'm just going to show a little one here. So performance data comparison on my laptop. Yeah, so nothing special. It's a 7200 single spindle something. No Fusion IO, no flash drives, nothing like that. 8 logical processors, 1 processor chip, 4 cores, hyper-threaded to 8. Okay, and hyper-threading is good. So we'll mention that. The hash join plan, the original plan the optimizer came up with on my machine, on my hardware, runs in 1,754 milliseconds. Okay? They're big tables, so that's not bad at all. That's pretty efficient. The parallel nested loops plan runs in 939 milliseconds. That's a lot quicker. And that includes the cost of creating the temporary table, populating it, running the query, and dropping the temporary table. I promise you. And the scripts are there for you to download and try on the Pulse website. I promise you, I was very fair, yeah, and parallel nested loops won. Now, on the right-hand side, there's a little table comparing the execution times of the two things at different DOP. Now, the hash plan is very variable if you look down those figures. Yeah, it's very variable. For example, DOP 5 is slower than DOP 4. DOP 8 is slower than DOP 7. There are a couple of reasons for that, but no good ones. It's an implementation thing, and you can get weird stuff like that. things that we have found in general is that parallel plans work best with an even DOP. Yeah? How weird is that? So DOP 1, DOP 3, DOP 5, DOP 7, for some internal reason that we would need the source code to find out, do not run as well, scale linearly, as the 2, 4, 6, 8. And 4 and 8 are my particular favorites, if you are at all concerned to know that. But the loops plan, on the other hand, scales really quite nicely. Okay, there's the same little effect between 4 and 5, but it's not actually slower, it's just only a little bit faster. But anyway, Adam Mechanic tomorrow morning, 90 minutes spotlight on parallel nested loops. They're awesome. Can be in the right circumstances. Okay, don't go get rid of all your parallel hash joins just because I said so. But they can work really, really well. But, and there's always a but, right? There's always an it depends. And is this the best plan? Yes, it might be. With no data in memory at all. So I had to fetch every page I needed for that query from my slow disk. So completely cold buffer cache, yeah? I don't know how realistic that is for you for a real query. But with a cold cache, hash join absolutely knocked the socks off it. 29 seconds versus 71 for the nested loops. Okay? Now there's some IO stats there. The thing I want to highlight is that in the nested loops plan, because it does iteration for that seek on the inside, it does 19,656 little scans on the inner side as compared with the hash join, which is just doing a big range seek type thing. So as a consequence, the hash join plan can issue larger, possibly, probably, if you've got your fragmentation right, more sequential read ahead. Yeah, so the pages need to come on the disk. The query processor can be much more aggressive about getting those pages into memory in advance of the need. On my laptop, and it is just a laptop, I saw 224K average disk bytes per read versus 36. So much larger reads with the hash join plan using aggressive read ahead, much smaller read ahead on the nested loops. Even though nested loops aren't as bad as you'd think intuitively, it doesn't wait to do the read ahead for each iteration. There is some prefetching involved, but it's not as good as the aggressive prefetching that can be done with merge and hash. Okay, does that make sense to everyone? Yeah, okay. Now, slightly different topic. It's often said that parallel execution improves response time but uses more CPU and memory. How many of you would disagree with that statement? Not many. Nobody. Oh, one person. Good on you. Not always. So here's an example. It's an example from one of my blog entries, actually. There's two tables, one with 5,000 random integers and one with 5 million random integers. And we're just counting how many matches there are. Okay? This serial plan with a simple hash match join and a stream aggregate to the count takes 920 milliseconds with 8,051 logical reads. Okay, seems pretty good, that's not bad. But if we execute exactly the same query at DOP2, we get this much more complicated looking plan. It's essentially the same plan. Yeah, so we've still got the hash match and the table scans, but we've got repartitioned streams, we've got a bitmap, we've got gather streams and a final global aggregate to add all the beans together, right? So that much more complicated plan running on 2 threads, just DOP2. Oh, there'll be more than 2 threads because of the zones, but DOP2, so only 2 schedulers at any one moment. 436 milliseconds of CPU, which is half the time of the serial plan, so it's twice quicker, you'd expect that. 220 milliseconds of elapsed time, 4 times better. So it's using fewer resources, it's using less CPU, half the CPU, and it's performing 4 times as well. Still with 8,051 logical reads. It's like magic. And the magic is the bitmap filter. You'll only get them in parallel plans. And the bitmap filter, as it's reading the rows from the top source into the hash join for it to build its hash table, it uses a number of hash functions and a Bloom filter to set some bits to indicate which values it's seen. Okay, it's not a one-to-one mapping, it's a Bloom filter, so there's a bit of science and magic going on. But effectively, it's a very good way to keep a record of which IDs you've seen. And then when the storage engine starts to scan on the probe side of the hash join, that bitmap is transferred over and applied during the scan. So that the only rows that come out of the scan on the lower side are the ones that could potentially match in the join. Okay? It's called early semi-join reduction. So it's eliminating rows before they even get to the join on the basis they cannot possibly join because the bitmap says they can't. Okay? Now, there can be some false positives, but never a false negative. It's a very powerful technique, but you can only get it in parallel plans, bitmap. There's a bit.ly link there if you want to read more about that. It's a very powerful technique. That's on the SQL blog. So, a bit more about CX packet then. Somebody asked a question earlier about that. For that DOP2 bitmap execution query, these are the latch and wait types that I saw from the DMVs. And you can see there are 660 milliseconds waiting on CX packet. That sounds terrible, right? 660 milliseconds out of whatever it was. That's awful. We should be concerned, right? Yeah, not so much. And the maximum wait time was 221 milliseconds, which is coincidentally quite close to the total execution time. So where did these waits come from, and should we be worried about them? Well, our final serial thread in that plan, because it's doing a count star, the final serial thread cannot get the first row of the result, which is the only row of the result, until the whole computation is finished. The whole computation is count star, or per group ID, or whatever. But it's going to wait there until the rest of the plan has done its work. It's got no choice. It can't join in and help. It's just got to sit there and wait for the first CX packet to come across the exchange. So even at DOP2, that query can have many worker threads active at any one moment. It could have, let's say, 6 worker threads for that plan. Okay? But because we specified DOP2, the execution engine will only let 2 of them run at once. Yeah? Otherwise, a single query with lots of worker threads could completely dominate the system. And if you said DOP2, then presumably you only wanted it to use 2 CPUs or 2 logical execution units. So it enforces that by limiting the query to 2 schedulers. Okay? So all those threads will be distributed across these 2 schedulers. So only 2 can be actually running at any one moment. Sounds bad, but that's what you asked for. You said to use 2 processors as best you can. And that's what it's doing. So the CX packet waits in this case are completely normal and inevitable if you think about it. Yes, question? Okay. Okay, so the question was, why, how do I know that DOP2 is optimal for this query? Okay. Okay. How do you determine that DOP2 was the optimum number of schedulers? For this query, I'm not saying that it is. The only point of DOP2 is it's the minimum DOP at which a bitmap can appear in the plan. Okay, because bitmap requires a parallel plan, so I just used DOP2. Okay. Now, obviously, I could have run further tests at DOP3, 4, 5, 6, 7, like I did earlier with the other things, and you would see a scaling, and at some point, starting all those threads, pushing it across exchanges, gathering all back together at the end, would get more expensive. So you'd lose more than you save. That's partially modeled, but a lot of it comes down to testing. Yeah. Okay. So CX packet waits, I was saying, are normal and inevitable because that final serial thread was waiting for 221 milliseconds for its first result to arrive. It has to wait that long. That's how long the query takes to produce its first result. And its wait type, they had to give it a wait type. What's it waiting on? It's waiting at the gather streams exchange for a CX packet to appear for it to process. So its wait type is CX packet. Okay? And as far as the other threads are concerned, only 2 can be running at any particular time. So one thread might be reading from the seek at the top and stuffing rows into a buffer on one particular exchange. Another thread might be doing the same thing elsewhere. And depending on which exchange buffers get full, it'll stop, yield control to the next thread that wants to run. SQL Server is cooperatively scheduled, so this is how it's supposed to work. There were more threads than we've allowed it to use processors, so there's inevitably going to be some waiting time. The point is to keep them short. Okay? The point is to keep them short and look out for any really nasty ones. If the parallel scan had distributed the rows really unevenly across the threads and one thread had done the majority of the work, the others would run out of work and sit there and wait on CX packet. So that would be a concern because they would be waiting for seconds, not milliseconds. So if you see 4 millisecond CX packet waits, however many you see, it doesn't matter. But if they're only 4 milliseconds long, which is the scheduling quantum, don't worry about it. It's probably completely normal. But if you see long CX packet waits, then yes, have a look at the plan, look at the DMVs, see where that waiting is occurring. Okay, so I've got about another 10 or 15 minutes. I'm just going to highlight a few of the less well-known problems that can come up with parallel execution. One of which Aaron might recognize in a moment. Okay, so for good parallel performance, we touched on this very briefly earlier on. Everything needs to be independent, yeah? So ideally, there'd all be separate connections, separate workers with no dependencies on any others, and they would just work as hard as they can, as much CPU as they can get, yeah? People worry when they see a system spike to 100% CPU. That's what I want to see as a performance tuning person, yeah? I want to see it spike really quickly to 100%, them all finished together, job done, yeah? Little spikes, good. I bought those CPUs for a reason, you know? Yeah. So short packet weights, as I said, if you've got long packet weights, it could be normal, but it can be tricky to investigate, because they could provide more metrics and more tooling in this area to make a sort of diagnosis easier. But if you think about it logically in terms of jelly beans and branches and zones and things like that, you can generally work out where it's going wrong. We'd like to see, in general, an even distribution of work across threads. It's not a golden rule, because one of the advantages of parallel scan is that it dynamically adjusts to the load on the machine. So say we have 4 threads running, and they happen to be 2 of them happen to be sharing a scheduler with another very busy query. So 2 of our threads aren't getting as much CPU time as the other 2. So with the demand-based parallel scan or parallel seek system, the first 2 threads will get more rows because they've got more time to get rows. All right, so you'll end up with a skew, which is actually by design, because you want to use all the CPU resources you've got. Now, I say in general it's good to have an even distribution of work, because you'd like to think that all your threads are fairly even, and if you come across a parallel sort or something which will have its memory grant evenly distributed across the threads, if one thread gets much more than the others, unexpectedly, because of this scan skew, it might have to spill to TempDB. It might run out of memory for its sort. It can't borrow the memory from other threads, because they're all independent. Once it's allocated, it's allocated. So bad things can happen if it's not evenly distributed, but it's not always a bad thing. If you find a parallel scan producing different, so one thread getting a lot more than others, look at the reason for it. It could be that the range is just too restrictive and there are not enough pages getting out there to distribute evenly across threads. But often the optimizer will recognize the possibility of this skew happening and put an extra repartitioning exchange somewhere in the plan to rebalance the work across threads. If you see a repartition you don't understand, generally speaking, it's there to rebalance the work across threads. It's not always a bet that pays off, but it's something the optimizer does have logic for. Okay. We also assume... Sorry, was that a question? No, it's just a phone. Yeah, we also assume even CPU time availability. Not always a practical thing. You might have 3 or 4 really long-running bulk loads or something going on in your system, which is tying up 3 or 4 schedulers. Yeah, SQL OS could be better written, I think, in my humble opinion, to cope with that sort of scenario. But if you get stuck on the same scheduler as a very busy process, you're not going to get as much time. There's no way for you to move off. Workers run from birth to death on one scheduler. They can't move, which is a shame. Okay. But also, ideally, we would like to see simultaneous thread completion. We'd like all our threads to start up at once, all to work as hard as they can, and all finish. That's the way the overall time is going to be reduced the most. Yeah? Makes sense, right? And we'd also like... Yes, question? Yes? Distinct counts? Yes. At the end, okay? Yep. So there's a question about optimizing distinct counts. All right, so we'd like unordered processing, because we saw earlier there is an overhead with merging exchanges. In the worst case, merging exchanges and preserving order is not just bad because the thread at the consumer side will have to check each one to say which one's next in sequence. That's bad enough on its own as an overhead. But you can even get deadlocks arising. And these are the same sort of deadlocks. They're detected by the same deadlock mechanism as you see with regular, X-lock, shared lock, whatever deadlocks. Now, SQL Server will detect deadlocks that happen like this, but it's very, very slow. Yeah, it can take 5 seconds for the deadlock monitor to wake up, and then it's got to work out how to resolve it, and then it spills all the CX packets, all the buffers, to TempDB to try and unjam the pipes. Yeah, it's not a thing you want to see. Unfortunately, in versions prior to 2012, it's very hard to see that you had a parallel deadlock. In 2012, you get a nice little warning icon like this. You see the little yellow warning triangle on the distribute streams? There's a red warning there that says, operator used tempdb to spill data during execution. And that's because the exchange buffers had to spill, physically written, all of them, to physical tempdb after possibly a 5-second wait while the deadlock monitor woke up to get this query plan to run. So what I've done here is I've written a very crafted query. I wanted to write the simplest query I could that would deadlock and show these exchange buffers going wrong. And all it does is read the first 30,000 numbers, integers, from a numbers table. You'll all have one of these, right? Phenomenally useful. Tally table, numbers table, something like that. It's just a sequence of numbers. One column. If you went to ITSIC, Ben Guns, Precon, you'll have one tomorrow. So it's just a very simple table of sequential numbers. And I'm just saying, give me the highest number that's less than 30,000. Right? That's a trivial query. It should complete just like that. Right? I get a parallel plan because I'm varying the max stop for this query, but I've forced a parallel plan by using an undocumented trace flag 8649. It's a very handy trace flag for testing only. Do not use it in production. It's undocumented, unsupported. You'll get wacky plans sometimes. But it's a great way of working out whether a parallel plan is possible or not. If you specify that trace flag, dbc trace on or trace off, or this query trace on shortcut, makes it fit better on the screen. Okay? Very, very useful trace flag, but as again, test only, just for educational purposes. So, this simple query, give me the highest number that's less than 30,000 from my numbers table that is clustered indexed on that number. At DOP1, it takes no milliseconds. I can't record it. At DOP2, it takes 4 and a bit seconds. DOP3, 3 milliseconds. DOP4, 8.8 seconds. Yeah? It's a disaster, but only at even DOP. Yeah? Weird. Weird, right? And the reason is this preserving of order. Because in this plan, we have a backward range scan from the clustered init seats which cannot be parallel, cannot be executed in parallel. The storage engine just doesn't support a parallel backward range scan for historical reasons. The first exchange is order preserving. The filter gets rid of all the even numbers from the stream. This is what my carefully crafted query does. And the final exchange is also order preserving. Now, if we watch the numbers from my table, and I've started at 100 going backwards. On the right-hand side, so they arrive from the serial seek, 100, 99, 98, 97, 96, all nicely ordered. Then they hit the first exchange, which is using round-robin partitioning. So every other row goes to a different packet for a different consumer. But it turns out, because it's DOP2, all the even numbers go to one thread, and all the odd numbers go to a different thread. All right? The parallel filter, remember there's two of these, yeah, serial in different colored zones. One of them is filtering out all the just the even numbers. Sorry, I got that wrong. So all the odd numbers are disappearing. And this final exchange, this gather streams, which is running the whole show, it's saying, get me the first row. In order to preserve order, it has to get one row from at least, from every input. It can't just take the first row from the first input and assume that that sorts first. It has to compare it to a second one to make sure that one's not higher or lower, right? But it never gets a row on that second stream because we happen to be filtering out even numbers. Now, this is a contrived example, and it's extreme, but I see this quite a lot. Yeah? I do see deadlocks quite a lot in production systems. It's not always this simple or this easy to work out. It's not always odd numbers and even numbers. But where DOP is even, we get this even, odd, and it all builds up. Yeah? So you get threads with even and odd only. When it's odd DOP, they get a bit more mixed up because it goes 1, 2, 3, 4, 5, 6, that sort of thing. So you don't get a deadlock. Does that make intuitive sense to everyone? There's a hand up there. So doesn't that indicate a fundamental flaw in the engine? Yes, I believe it does. I'm sorry, I talked over you. What did you say? Yeah. Right. So the statement was that if not, one of the producers has no rows, you ought to communicate that somehow. Yeah, that's right. Yeah, I tend to agree with you. Yeah, that'll be a flaw right there. Yes. Right, there was a complicated question. I'm not sure I'm going to summarize it for the recording. Let me just reply by saying this plan does have separate zones, and yes, adding that communication would make things more complex, and I can sort of understand why they haven't done it. All right, and it probably doesn't come up enough in practice for them to go out and fix it. But it's not the only parallel bug there's been in SQL Server, or limitation, I should say. But in terms of whether it should wait for a first row, you have to remember that query plans are cursors. All right? So they start execution at the right-hand side. The first operator to run is that gather streams, and it asks its filter, or one of its filters, for a row. It asks the distribute stream for a row, and so on. So the rows appear to flow right to left, like we're all used to reading query plans. That's the direction of the data flow. But in terms of the programmatic execution of the plan, it's being pulled. Yeah? And I like Rob Farley. He's an MVP from Australia, if you don't know him. He sang at Pass Summit last year. I like the way he describes this. He says that, Rob Farley, there he is. Execution plans suck, right, Rob? Yeah. Execution plans suck. I like that. Because they do. They suck rows. Yeah? And it's a row at a time. That's an iterator model. So they are fundamentally cursors. Yeah? So all your set-based programming ultimately comes down to very efficient, iterative cursors. Okay, so that's a deadlock. There's more description here on the slide, which I'm not going to read out to you, but it essentially goes through the details of exactly how that deadlock arises. By the way, I'm very proud of that query plan. That was quite hard to produce that demo for you. So just wanted to acknowledge myself there. Okay. I think probably the last thing I want to show you, and then we'll take some general questions, is a couple of bugs that are not yet fixed in 2008 onwards. These were fine in 2005. Yeah? So progress sometimes means new bugs. And it involves the top operator in a serial plan. When it's after a gather streams, the top, because the execution plan is sucking and row by row, eventually the top will get all the rows it needs, but the rest of the stuff all running independently is still merrily producing rows, filling packets, doing all the good things that it does. But the top has to say to the other things, hey, that's enough. Okay? I've got all the rows I need. We can finish execution now. Please all close down, shut down, tidy up after yourselves, that sort of thing. And in general, that works very well. But there are some scenarios where, with a top and a gather streams, one or more threads may not get the signal to stop. Okay? The little fraction of a query plan here is a query from my parallel plan suck blog post, which selects the first million rows from a table source. Okay? And one of the threads never stops. And it's a potentially huge result set. And one thread ends up processing 333 million rows because it never stops. It never gets the stop signal. So to produce those 1 million rows the query needs, it runs for an absolute lifetime because there's signaling breakdown. And the second one I wanted to mention, so beware of top with parallelism. In some cases, there is a bug there. The second one is the one that Aaron discovered not too many weeks ago, was it? Yeah, something like that. With a parallel plan, if you've got statistics I/O turned on, and I hope you're not just tuning on I/O, but you'll be taking account of it, so that's okay. But if you set statistics I/O on with a parallel plan, quite often, especially at low DOP, you will see a ridiculously small amount of I/O. It'll underreport it from millions down to 10 or 20 or 30. Aaron has a great blog post on it at bit.ly misleading I/O, which I encourage you to read. Just something to be aware of if you're tuning parallel plans that way. Final slide. Yeah, final slide. Reasons that you may not get a parallel plan when you're expecting one. Okay, you can try that trace flag, 8649 that I mentioned, if you just want to check to see whether a parallel plan is possible. It's not foolproof, but it is very, very good at eking them out. Reasons you may not get a parallel plan when you're fully expecting one. You've got a big, expensive query, and suddenly you get a serial execution plan. Nothing more frustrating. So one reason that your whole plan must be serial is some limitations. If you modify a table variable, you'll get a fully serial plan. You can read from a table variable in parallel, that's fine. You cannot insert, update, delete, merge, whatever. If you do that, your whole plan will be serial. Something to bear in mind. T-SQL scalar functions, which are brutal and evil and should never be used, except under license in any case. If you use a scalar function, so that's a function with a begin and an end. Yeah? Yeah. Rob's smiling. That's another one of his talks. Anything with begin and end is bad. It's a procedure, not a function, right? Yeah. Certain built-in functions, like object name, if you put object name in your query, it'll suddenly stop being parallel. I do not know why, but it's one of those things. And if you access a system table at all, yeah, so any access to sys. Whatever, fully serial plan. And now some of these things do change over time, but I checked this out in 2012 and it's still the same. You get a serial branch in a plan, so you get a nice parallel plan, lots of workers running independently, producing results at awesome speed. But then all of a sudden you'll get a gather streams, a serial section, and a distribute streams. And that serial section can be a real bottleneck, right? And you might get one of those if you have a T-SQL multi-statement function, a global top or aggregate, something that has to produce a top or an aggregate across all threads. Backward scans, like I mentioned. For some reason, the storage engine never implemented a parallel backward scan. We should probably request it on Connect or something, I don't know. But they've never implemented it, I don't know why. So in some plans, you'll see a parallel forward scan followed immediately by a sort to reverse the sort order because it can't do a parallel backward scan. Something to watch out for. And recursive CTEs. There's lots of examples, actually, but recursive CTEs are something else that can't currently be run in parallel. And I imagine that's because it probably makes my brain melt just trying to think how you would run that in parallel, right? Yeah. Other optimizer things. You may not get a parallel plan you're expecting because the best plan was a parallel nested loops plan, and it doesn't cheapen the inner side. It doesn't reduce that CPU cost, as I think it should. Yeah, I mean, there are multiple workers running at the same time, concurrently, yeah? To me, that is parallel execution, and it should reduce the CPU cost. It doesn't. No doubt they have reasons, and they don't want to change it now because it will screw everyone's cached plans up. But it's frustrating, right? Frustrates me. Also, you may have your cost threshold set too high. That's an obvious one. Yeah, if the optimizer guesses that your plan costs 6 units because of some estimation error in cardinality or some other limitation, it gets it too cheap, and your threshold is set to 35 or 50 or whatever, you'll never get a parallel plan. The other reason is that the optimizer might have come across what it considered was a good enough serial plan that was, pretty cheap, looked pretty good, didn't justify searching more to find a little bit faster, in its opinion, parallel plan. Frustratingly, the difference between a little bit faster parallel plan and the slightly cheaper serial plan in many practical cases is orders of magnitude. So it's another big frustration with me. In real tuning work, I see a lovely parallel query, I change one thing, bang, serial plan. Yeah. So 8649 and a plan guide. Yes, question. Yep. Yep. Yeah, so the question is that sometimes you see parallelism and hash join in particular engage too early over a much quicker serial plan with maybe a lookup or nested loops. Yes, again, you have my sympathy. The costing model is not perfect. It tends to massively over-cost key lookups in particular and iterative things. It assumes every query when it's costed. Come to my half day on the Query Optimizer on Friday and I'll tell you all about it. But it assumes that every query starts with a cold cache. There's no data in memory at all. It assumes every page it's going to need is going to have to come from disk at some point, and it costs accordingly. Yeah. So if your query happens to be really fast when stuff's in memory, yeah, that's the reason for its decision, and it's not always right. It's a very general model, and it gets stuff wrong. That's why we have hints and plan guides and experts. Yeah. Sometimes you can write the query in a different way. Sometimes you can use an intermediate table. There's lots of tricks you can use. Yeah. But sometimes you just have to force it. And hey, I do know better than you. All right. So just a quick word about all the wonderful things that Parse does. This slide needed to be in my deck, so there it is. They do free SQL Server stuff all over the place. SQL Saturday, I love those. Rally, I'd like to go to one. The Summit, you're at. And finally, thank you.